So hello students, welcome to today's class. Today we are solving some problem related to Wronskian and other theorem that we have already done in our previous classes. So we are taking one problem. This is so that the solution e to the power x, e to the power minus x, e to the power twice x of this homogeneous equation y triple dash, that means triple differentiation of y minus 2y double dash minus y dash plus twice y equal to 0 are linearly independent. Next step, we have to find out our solution of the given equation. So first, how to do? First, we are solving this equation. First, we are writing the given equation here. Given equation is what? Y triple dash minus twice y double dash minus y dash plus twice y equal to 0. Mark it 1. And we are given to show that e to the power x, e to the power minus x and e to the power twice x are three solutions. So we are supposing y1x equal to e to the power x, y2x equal to e to the power minus x and y3x equal to e to the power y3x equal to e to the power twice x. Now taking first one, this is y1 x equal to e to the power x. Therefore differentiate it, y1 dash say e to the power x and y1 double dash, we are differentiating double, so it again become e to the power x, and y1 triple dash, it is again e to the power x. If y1 be a solution of equation 1, then y1 must satisfy the equation 1, that is, then we must have y1 triple dash minus 2 y1 double dash minus y1 dash plus 2 y1 equal to 0. Now we have to see it satisfies or not. Now y1 triple dash minus 2 y1 double dash minus y1 dash plus 2 y1. Putting the values of y1 dash, y1 double dash, and 1 y1 triple dash. So it becomes e to the power x minus 2 e to the power x minus e to the power x plus 2 e to the power ultimately 0. So from this we can say that hence y1 is a solution of what? Equation 1. Or similarly, if we take y2 equal to e to the power minus x and y3 equal to e to the power minus twice x, then both are satisfies equation 1, and hence we can say that y2 and y3 are also solution of equation 1. Similarly, e to the power minus x and e to the power twice x are also solution of 1. Now we are given to show that these three functions are linearly independent. So for linearly independent, we have to find out the Wronskian of, that is the Wronskian of x, or Wronskian of these three functions y1, y2, y3. That is, we can write using determinant. First function y1, first row, y1, y2, y3. Then the derivative, first derivative y1 dash, y2 dash, y3 dash, then y1 double dash, y2 double dash, and y3 double dash. Putting the values, we are taking e to the power x, y1, e to the power minus x, e to the power twice x. Similarly, derivative e to the power x minus e to the power minus x to e to the power twice x. Then again derivative y1 double dash e to the power x, e to the power minus x, 4 e to the power twice x. So we have to find out the value of this determinant. We are taking common e to the power x, e to the power minus x into e to the power twice x. From each column So this becomes 1, 1, 1, 1 minus 1, 1 minus 1, this is 2, again 1, 1, 4. Now we will use e to the power twice x, this is 1, and now use the elementary transformation. So we are doing C2 minus C1, and in C3, that is column 3 minus column 1. First column remains same, so we are subtracting C1 from C2. This is 0, minus 2, 0, 0, 1, 3. So in the first row, two elements are 0, so we can easily expand. So after expanding, we are getting minus 6 minus 0, ultimately minus 6 e to the power twice x, which is not equal to 0 on the interval minus infinity to infinity. So since the Wronskian of these three functions y1, y2, y3 is not equal to 0, so we can say that y1, y2, y3 are linearly independent solution of what? Solution of 1. Since the order of the given equation is 3, so the general solution will contain 3 arbitrary constants. If C1, C2, C3 are the arbitrary constant, if these 3 are the arbitrary constant, then the general solution is given by, so the general solution is given by, we have already have one theorem, y equal to C1 y1 plus C2 y2 plus C3 y3, that is y equal to C1, y1 is e to the power x, C2 e to the power minus x plus C3 e to the power twice x, and this is your general solution of the given equation. So this way this type of problem can be solved. Next we are taking another problem which is given like this. Show that y1 equal to sin x and y2 equal to sin x minus cos x are linearly independent solution of this equation y double dash plus y equal to 0. Here determine the constants c1 and c2 so that the solution sin x plus 3 cos x equal to c1 y1x plus c2 y2x. From this relation we are given to find out the solution. So we are given to find out the solution, not solution, we are given to show that these two are independent solution and value of arbitrary constants c1 and c2. The problem is similar to the previous one. Here given equation is y double dash plus y equal to 0. We are marking it 1. So y1 equal to sin x. Since y1 equal to sin x, therefore y1 dash, this is differentiation of y1 equal to cos x, and y1 double dash equal to minus sin x. So if y1 be a solution of this given equation, then y1 must satisfy this equation, and for this we must have y1 double dash plus y1 equal to 0. Now it is y1 double dash and y1 equal to what? So putting the value of y1 double dash and y1, this is minus sin x plus sin x, ultimately 0. So it satisfies the equation. So y1 is the solution of 1. Similarly we can show that y2 equal to sin x minus cos x is also solution of 1. By the same process we can show that y2 equal to sin x minus cos x is a solution of 1. Now for the function are independent or not, for this we have to find out the Wronskian. So Wronskian of x. So here the given function is y1 and y2. So first row y1, y2, second row derivative of y1 dash and y2 dash. Putting the values, y1, y2 is sin x and sin x minus cos x. So derivative of sin x, this is cos x, sin x is cos x, and cos x minus sin x, ultimately plus sin x. We are expanding this determinant, so after expansion it becomes sin x cos x plus sin square x minus sin x cos x minus minus plus cos square x. So ultimately 1, which is not equal to 0. So Wronskian of these two functions y1 and y2 is not equal to 0. So we can say that y1 and y2 are linearly independent solution of 1. So y1 and y2 are linearly independent solution of what? 1. So first part, it is given that sin x plus 3 cos x c1 y1x plus c2 y2x. Here we given y1x equal to sin x. We are taking earlier c2, or given, it is already given, c2 equal to sin x minus cos x. So we are comparing, just putting the, now we are comparing the coefficient of sin x and cos x from both sides. So after comparing the coefficient of sin x cos x, we are getting c1 plus c2 equal to 1. That is the coefficient of sin x is left on right hand side c1 plus c2 and left hand side is 1. And coefficient of cos x, this is minus c2, and coefficient of cos x equal to 3. From this we can say c2 equal to minus 3, and after calculation this is c1 equal to 1 minus minus 3 equal to 1 plus 3, this is 4. So in this problem c1 equal to 4 and c2 equal to minus 3, and this way so our next problem is this: find the Wronskian of the function y1 sin x and y2 sin x and find whether or not they are linearly dependent. So first one, we are given to find out what is the Wronskian of these two functions y and y2. If the Wronskian is 0, then it is dependent, or otherwise it is independent. So one more portion is there also from the differential equation. So the first part we have already done in our previous problem. What is that? So here y1 equal to sin x and y2 equal to sin x minus cos x. For linear dependence or independent, we have to find a Wronskian of x. This is y1, y2, y1 dash y2, and sin x. The function are same in as like our previous problem. So we are getting Wronskian is 1, which is not equal to 0. So y1, y2 are linearly independent. So next part, we have to form the differential equation. So y1, y2 are linearly independent. So the general solution, is given by, so we have a theorem that the general solution is given by y equal to c1 first function plus c2 y2. These are two linear independent solutions, so we can write y1 equal to c1 y1 and c2 y2. So here y1 is sin x and y2 is sin x minus cos x. So mark it 1. Now we differentiate. So differentiating equation 1 twice. So after first differentiation, c1 cos x plus c2, this is cos x plus sin x, and second differentiation y double dash minus c1 sin x plus c2 minus sin x plus cos x. We are marking it 2. So if we add 1 and 2, adding here obviously C1 and C2, here obviously C1 and C2, C1 and C2 are parameter. Here obviously C1, C2 are parameter. So after adding 1 and 2, we have y double dash plus y equal to 0. After addition, we have y double dash plus y, then all are cancelled on the right hand side, so it becomes 0. And this is the required differential equation, and this is your required differential equation. So in this way we can show two functions are linearly dependent or not. If linearly independent, so we can write the general solution y equal to c1 y1 plus c2 y2, and from this after differentiation adding we get y double dash plus y equal to 0. So this is your required differential equation. Taking another example, show that sin x cos x and sin x minus cos x are the solution of the differential equation y double dash plus y. These are similarly as we done similar portion as we done in our previous problem, where y dash equal to dy by dx. Prove that these solutions are linearly dependent. In this case, we have to prove that these solutions are linearly dependent. For this, Wronskian of these three functions must be equal to 0. So here the given equation is y double dash plus y equal to 0. So we are taking as similar to as earlier, y1 equal to sin x, y2 equal to cos x, and y3 equal to sin x minus cos x. Now y1 equal to sin x, y1 dash equal to cos x, and y1 double dash equal to minus sin x. So if y1 is a solution of this equation, then it must satisfy equation 1. For this, we have to we are seeing y1 double dash plus y1 equal to minus sin x plus sin x equal to 0. Therefore y1 is a solution of this equation. Similarly, we can prove that y2 equal to cos x and y3 equal to sin x minus cos x are also the solution of the given equation. Now to find the Wronskian of this function, this is Wx, Wronskian of these three functions. These are y1, y2, y3, y1 dash second row, y2 dash, y3 dash, y1 double dash, y2 double dash, y3 double dash. So putting the values, y1 is sin x, y2 is cos x, and y3 is sin x minus cos x. So next step, y1 dash, this is differentiation of sin x is cos x is minus sin x, and this one is sin x is cos x minus plus sin x. Next, y1 double dash, again if you differentiate cos x, this is minus sin x minus cos x minus sin x plus cos x. Now we have to find the value of this determinant. Before multiplication, we are using elementary transformation. So we are doing in row 3 plus r1. So first two row remains same because we are doing elementary transformation on third row. Cos x plus sin x, and this becomes r3 plus r1, sin minus sin x 0, minus cos x 0, and minus sin x 0, cos x minus cos. Ultimately the each and every element of third row is 0. So ultimately this is 0. So in a determinant, if each element of a row or column is 0, then the value of the determinant is 0. So Wronskian of x, that means Wronskian of function y1, y2, y3 are 0. Hence from this we can conclude y1, y2, y3 are linearly dependent, and this prove our problem. So we are given to show that solution are linearly dependent. We have shown that this solution y1, y2, y3 are linearly dependent. Okay, thank you.